Have you ever wondered why two people can eat the exact same meal, and while one person's body just seamlessly processes all that energy, the other seems to hit a complete wall of metabolic gridlock? It's a question that gets right to the heart of human health. The answer? Well, it lies in whether your body operates like a highly tuned hybrid engine or one that's kind of stuck in a single gear.
Welcome to this explainer. Today we're looking at the 24-hour metabolic engine, fuel, fasting, and flexibility.
Okay, let's dive into this. We're talking about metabolic flexibility, which is essentially your body's ability to respond or adapt to changes in energy demand. But here's the wild part. You know where this term actually comes from? It wasn't coined by sports scientists. It was first used way back in 1985 to describe the helminth. Yes, a parasitic worm. Scientists noticed this little guy had the incredible capacity to generate energy either aerobically or anaerobically, adapting flawlessly to chaotic changes in its host's habitat. And honestly, humans require that exact same kind of biological versatility.
To understand our own versatility, we need a roadmap. Over a 24-hour period, we're going to track how the body communicates across 4 different states: sleeping, eating, resting, and exercising. Think of your skeletal muscle as the engine, and your white adipose tissue, your body fat, as the fuel tank. A healthy metabolism? It absolutely requires constant, dynamic communication between this engine and this fuel tank.
Section 1. The night shift, sleep, fasting, and circadian health.
So let's start our 24-hour clock at midnight. When you go to sleep, your body enters a profound fasting state. But this isn't just downtime. It's a highly active biological process that relies heavily on biological timing. The American Heart Association points out that circadian health requires the alignment of our internal systems to the light-dark cycle. The really crucial takeaway here is this: sleep timing regularity is as important as sleep duration. Your metabolic engine literally requires regular, predictably aligned downtime to function optimally. If your sleep is erratic, that critical communication between your muscle and your fat, it starts to break down before you even wake up.
Now, while we're sleeping and fasting, our body relies on lipolysis, breaking down fat, just to keep us alive. Which leads to this absolutely mind-blowing fact from the source data. A normal weight, completely healthy woman can actually have the exact same amount of white adipose tissue as an obese man suffering from type 2 diabetes. No way, right? But why does this matter? Because it proves that metabolic health is not strictly about the amount of fat you have. It's entirely about how healthy, sensitive, and adaptable that tissue is overnight. Healthy fat acts like a generous supplier of fatty acids while you sleep. Unhealthy fat, it hoards it or releases it at totally the wrong times.
Section 2. Breaking the fast. Transitioning from fasting to feeding.
As the sun comes up, we eat, and this is the first major transition of our day. The moment you ingest food, insulin spikes, and your hybrid engine has to instantly stop burning fatty acids and shift gears to store incoming glucose. Looking at the rapid movement or flux of free fatty acids in and out of adipose tissue across 3 meals, we see a stark contrast. For lean, metabolically flexible individuals, there are dynamic spikes and drops. Their tissue rapidly stores dietary fat after a meal, clearing out the bloodstream. But for obese individuals facing metabolic inflexibility, it's basically a flat line. Total metabolic gridlock. Their tissue resists storing the fat, leaving those fatty acids lingering in the bloodstream where they can actually cause insulin resistance in the muscles.
Zooming out to your whole body, we measure this adaptability using something called the respiratory quotient, or RQ. Simply put, a lower RQ means you're burning fat, and a higher RQ means you're burning carbohydrates. Notice how a healthy response acts almost like a roller coaster, dropping low during sleep to burn fat and spiking right up after breakfast for carbs. Conversely, look at a patient with type 1 diabetes. The response is rigid. It's stuck in a high carbohydrate burning gear all day and all night. This perfectly illustrates the danger of a metabolically inflexible engine. It literally loses the ability to choose the right fuel for the right moment. But you know, eating and sleeping are just the baseline. What happens when we push the pedal to the metal? Rigorous exercise demands an incredible 25-fold increase in energy expenditure compared to when your body's just resting. 25 times.
Section 3. The ultimate stress test. Shifting gears for exercise.
When you start working out, your skeletal muscle suddenly requires upwards of 95% of your body's total energy. This is the ultimate test of metabolic flexibility. So, how does our hybrid engine flawlessly open all the valves to keep us moving? Well, first, intense demand taxes your local energy stores instantly. Your body releases adrenaline, which acts like an emergency alarm, spiking fat breakdown in your white adipose tissue. Those fatty acids are then rapidly mobilized into your bloodstream to feed those working muscles. Your body is basically a smart hybrid car. Doing high-intensity sprints, it relies heavily on burning glucose.
But as your workout goes on, it smoothly transitions to rely mostly on fat.
And this brilliantly illustrates just how adaptable a well-trained engine can be. When subjects were essentially hooked up to an IV and given a lipid overload, basically a massive influx of fat, the trained athletes massively ramped up their fat oxidation to clear the overload. But more importantly, because they burned the fat so efficiently, they were able to preserve their precious muscle glycogen stores. The untrained subjects, on the other hand, they couldn't burn the fat, and their glycogen stores just plummeted. Training literally teaches your muscles to protect their premium fuel by happily burning whatever else is available. Section 4. Rewiring the system. How to build a flexible engine.
So if we're currently a bit inflexible, how do we actively fix it? Let's talk about rewiring the system based on the source data. In the medical community, you usually hear about two main interventions: eating less or moving more. Now, calorie restriction absolutely leads to weight loss, but according to the research, it does not enhance the skeletal muscle's underlying capacity to burn fat. You basically just get a smaller engine, not necessarily a more flexible one. Exercise training, however, pure magic. It enhances insulin sensitivity, increases the actual mitochondrial capacity of your cells, and radically improves your body's ability to oxidize fat. While both approaches have health benefits for sure, only exercise truly rewires your muscle's metabolic machinery from the inside out.
Which leaves us with one final provocative question. Can a pill replace exercise? Pharmaceutical companies have spent billions trying to create exercise mimetics, drugs that mimic the effects of a workout. There was even a huge controversy around a drug called melandrate, used to alter fuel utilization in the heart, with some athletes hoping it would boost their performance. But the data from our sources asserts a pretty hard truth. A true exercise mimetic is nearly impossible. Why? Because you can give a patient a pill to release fatty acids, sure, but without the physical act of exercise creating a massive demand for that energy, the fuel just sits in the bloodstream causing gridlock. True metabolic flexibility requires the irreplaceable biological magic of physical movement. You literally have to rev the engine to keep it flexible. Thanks so much for joining me on this explainer, and I really hope this leaves you inspired to go out and stress test your own hybrid engine today.